Electron affinity. The definition of electron affinity is very similar to that of ionization energy. This is also the energy required to remove electrons from an ion, but this time around we are removing electrons from an anionic ion. And in the case of the first electron affinity, we're removing an electron from the negatively charged anion, yielding the neutral atom. But if we were dealing with the second electron affinity, we'll start with a 2 minus anion yielding the 1 minus anion. Much like ionization energy, you're going to have a change of a 1 charge from reactant to product, but you start from anions in the case of electron affinity. And this is the physicist's definition: the energy required to remove electron from an anion, which works pretty well for what we're going to be doing here in terms of calculations. Now, the one thing to be stated right here is that unlike ionization energy, the electron affinity can actually be negative or even zero. But whenever the values are greater than zero, what that tells you is that you actually have to put in energy to remove the electron from the anion. And that would only happen if the electron is indeed attracted to the nucleus in an effective manner. If that weren't the case, then you wouldn't have to put in any energy for the electron to come out. Now, the trend, as you'll see in a second, tends to, going from left to right, it tends to increase much like the ionization energy, and that's due to the effective nuclear charge. From top to bottom, the electron affinity decreases because the ionic radius increases. So the same ideas associated with ionization energy apply to electron affinity. And looking at the table now, including the electron affinity values in kilojoules per mole, what we see is that going from top to bottom, indeed, there is a decrease in the electron affinity. For the alkali metals, we go from 73 kilojoules per mole for hydrogen all the way down to 46 kilojoules per mole for cesium. Looking at the halogens, we start at 328 kilojoules per mole and we go down to 270 kilojoules per mole once we reach astatine. So from top to bottom, we tend to see that decrease, much like we saw for ionization energies, which is completely correlated with the size, the increased size of the elements. And going from left to right in the periodic table, generally speaking, we see a decrease in the electron affinity, but there's some interesting aspects, some interesting features that do take place here. So looking at the second row, we see that there is a decrease going from lithium to beryllium, but then we increase the value up until carbon, and then we decrease it again, increase it one more time, and yeah, so we keep increasing this. So even though the original trend is that the electron affinity ought to be increasing from left to right, we're actually seeing a little bit of discrepancies happening. Specifically, we see it for beryllium, and then we see it for nitrogen. Okay, so those are the ones that are kind of, oh, and neon, definitely neon. So beryllium, nitrogen, and neon are destroying that trend a little bit, going from left to right. The other feature too is that now we begin to see those negative values present, right? So let's take a look at beryllium, nitrogen, and neon a little bit more carefully. The configuration of beryllium is 2s2. That of nitrogen is 2s2, 2p3, and neon has a configuration of 2s2, 2p6. Drawing out the configuration shows that beryllium has a full shell within the 2s orbital, and it doesn't have any more room to accommodate electrons in the 2s orbital itself. If you were to gain any electrons, they will have to be placed on the 2p orbitals, which are higher in energy. So not as good a situation. For nitrogen, we have every single box in the 2p's already filled up with one electron. So if we were to place another electron, we will have to now pair it up with the first electron that we had there, creating some electron-electron repulsion. Once again, not a favorable situation. And for neon, the 2p orbitals are completely filled up with electrons. So you can't even fit an electron here. So it's not even a question of electron-electron repulsion. the Pauli exclusion principle prevents an additional electron being added to the 2p shell. So that means that the next electron will have to be added to the 3s orbital, which is much higher in energy, simply because the energy level, the principal quantum number, is higher. So each one of these explanations tells you why you have this discrepancy in electron affinity. The fact that beryllium has a negative um, electron affinity means that it doesn't want to get the electron because it has to put it in a higher energy level. The same explanation goes for neon. And for nitrogen, the reason you don't want to have that extra electron is because you're pairing it up with extra electrons that were already present there. All right, now, as we can see from the table, the elements that have negative values, like the alkaline earth metals, nitrogen, the noble gases, um, and then elements like manganese, hafnium, zinc, cadmium, mercury, and ytterbium, all those values that are either zero or negative tell you that there is no benefit to having an electron present to form an anion with these elements. So they don't form anions by themselves. You can force them, at least initially, to form that anionic charge if you provide some other means of energy stabilization by creating ionic salts, something that we're going to discuss in future lectures. But by itself, nitrogen doesn't actually want to get an electron. And none of the elements highlighted here on the periodic table want to get any extra electrons. They don't want to form anions. The second thing to be noticed is that if you do have second or third electron affinity values, irrespective of whether the element had a positive first electron affinity or not, the second and third electron affinities are all negative. And this is basically a result of the fact that the moment you place the first electron to form your 1 minus anion, you already have a negative charge present in your ion. And trying to bring a negatively charged electron into a negatively charged atom becomes more and more difficult, which is the reason why the second and third electron affinities are negative. Third point, out of all the values here, notice that the halogens have the highest electron affinity values. And because of that, what you're basically saying here is that the halogens have a high interest in acquiring electrons. And they tend to be very corrosive substances if you have them in their elemental form, because they're on the lookout to get electrons from everything else. And the values of electron affinity are high enough that it's very easy for the halogens, especially fluorine and chlorine, to remove electrons from most anything else, which is one of the reasons why they are dangerous to handle. The last aspect of this, and perhaps this is going to be the one that may blow your mind a little bit, at least it did for me when I realized what I was looking at, is the fact that when the electron affinity values are positive, you can actually form a stable anion. And it turns out that the vast majority of the periodic table can actually form stable anions, and most of them are metals. So things like lithium minus, sodium minus, they actually do exist. In the typical conditions that we carry out in the lecture labs, you don't typically have the right equipment to make them happen. But if you did have inert atmospheres and the proper equipment, you could actually create sodide or lithide or potaside. Those things are not just hypotheticals. Scientists have actually made them in the past and isolated them and actually characterized them crystallographically. So it's kind of amazing to think of the metals as actually forming stable anions. Now, needless to say, I'm not going to actually use that premise to like have you do nomenclature, because you can get pretty confused at that point. But if you actually were to go into chemistry as a field of study, you would actually get into those topics of discussion. It's actually kind of cool to see that, yeah, metals can actually end up forming anions. Okay, the last thing to be said about electron affinity is that you could still apply the Balmer-Slater approximation to calculate the electron affinity for elements. But here I'm going to show you that for the second electron affinity of oxygen, if you apply the same logic, right? So second electron affinity means that you are going to start from the O2 minus anion, and you're going to remove an electron to become O minus. And so the O minus is the final state, the O2 minus is the initial state. And if you use Slater's rules to group the electrons and determine the shielding constants, followed by determining the C effective nuclear charge, and then use the Balmer-Slater approximation, you will get a value. But turns out that even for oxygen, the value you get is really bad in terms of the experimental error. The actual value is 14 kilojoules per mole, whereas the calculated value is negative 1614, yielding a percent error of 117. So needless to say, whereas for ionization energy, I will have you use the Balmer-Slater approximation to calculate the value. I will not have you do that for the electron affinity. The error is just too great. And this is actually kind of on the conservative side. There's other elements for which the error is even a lot greater than this one. So we will not be using this approximation for the electron affinity. We will use a different technique to find that value. But I will save that discussion for the following video. So for now, see you next time.